lots of natural disasters triggered by that core not working properly, and therefore there was this bunch of pseudo scientists. They wanted to bring the core back to normal speed, let's say. So I want to introduce today's talk by talking about this, because I want to show you what this, why is this unrealistic, and why this is important for plate tectonics. So it is unrealistic because we can understand easily by looking at the structure of our planet. And this structure is composed of shells. So it's 1, 2, 3, 4 different shells. And each one of these is characterized by specific mechanical properties and also temperature. So the temperature is what I want you to focus today by looking at this picture. And in particular, the outer shell of our planet is called a lithosphere, and is characterized by temperature that goes up to 1300 degrees Celsius degrees. So relatively cold from a geological perspective. Below this kind of thin shell, which goes down to probably 200 kilometers at depth, we find the mantle. So mantle is much thicker layer, and it's composed of solid rock. It's mainly olivine. But again, I want you to focus on the temperature. So here we are going from 1300 degrees to about 4000. So, and the temperature, of course, increases progressively the more, the deeper you go into towards the center of the planet. At depth larger than the mantle, we find the outer core. So the outer core was the famous core that the movie was mentioning. And according to the movie, that core was stopping from spinning. So we'll talk about that in a moment. But just look again, the temperature is 4000 degrees, so pretty hot. And then we go even deeper and we find the inner core, which is about 5000 degrees. So all this structure of the planet tell us that our planet Earth is still very, very hot and alive. There is a number of planets on the planetary system that are, geologically speaking, they're dead planets because they're cold. And the fact that we have this gigantic amount of heat, which is energy, this energy trigger a number of processes on our planet. One of those is the topic of today's talk, which is plate tectonics. So the fact that we have this core spinning is because the entire planet is spinning. So one of the big mistake, or I don't know whether it was a mistake, but this unrealistic geological scenarios that I was mentioning about the movie The Core, was that the core in our planet is spinning, but just because the whole planet is spinning. Now, what is actually moving down there it's a number of vortex that are actually occurring within the outer core. And that's because the outer core is essentially made of nickel and other metals, but they are under liquid conditions. So imagine some liquid that is 4000 degrees Celsius. So that would create a number of vorticity, a number of motion within that core that actually triggers a number of other processes. So the fact that this motion of the outer core was stopping, according to the movie, was unrealistic, because it's essentially the heat itself that is creating the motion. So maybe in 5 billion years, maybe even more, this whole heat that is now stored in the core will be released progressively towards the outer shells of the Earth, and the whole planet will actually be a cold planet like other planets on the planetary system. And at that time, then yes, we can have actually all the phenomenon, the catastrophes that are depicted in this movie. But until then, our planet is still very, very alive, and that fact that it's alive is given by the temperature. So why I'm mentioning this, and what is the relationship between this and plate tectonics? And the relationship is very simple, because this immense amount of heat actually can allow rocks to flow. Even if they are solid rocks, they can actually flow as they were fluids. So I will mention this about how this actually occurred in a moment. But one of the first effect of this generation of this heat of the planet is actually the generation of the magnetic field. The magnetic field, in fact, is one of the first most evident products of this heat that is generated in the outer core, which again is liquid. So all the vorticities, all the motion of this nickel and other elements, metallic elements that are contained in the outer core, together with the spin of the planet around the spin axis, generates this magnetic field. That actually, the magnetic field is not just useful to navigate. So, for example, to have a compass and allow us to navigate in, for example, in oceans, but also it's very important because the magnetic fields protect us from very dangerous particles that are released from the sun continuously. Those particles are called solar winds, and during what we call solar storms, they are released and are pretty much projected towards our planet. And the only fact that we have an atmosphere, which is extremely thin, just surrounding our planet, is because we have the magnetic field. Without the magnetic field, we wouldn't have an atmosphere, and that wouldn't really allow life on our planet. So it's a very simple process, but so critical for our life on this planet that you might not have realized about this before. So the second effect of this generation of this heat that is stored in our planet is, as I promised, is plate tectonics. So plate tectonics is a very simple theory that describes our planet as divided. The outer shell, which is called a lithosphere, has divided into a number of rigid blocks that we call tectonic plates. And those tectonic plates can actually move around the planet. There is no such a plate that is still on our planet. They are all moving in different directions, and because of that, they interact with each other. So the fact that they interact with each other, they can create and trigger other mechanisms and other processes that we can look every day, and I will mention that in a moment. But first of all, let's see why can plate move. So plates can actually are only the superficial part of the outer shell. So again, what we call lithosphere. So it's the lithosphere that is broken up in pieces. But below lithosphere, if you remember the first slide, is other mantle, and that mantle it's solid. So there is no such a liquid part in that portion of the planet. So why can plate move? So the fact that they can move, like in this picture, is because the temperature. So again, that huge amount of energy that is stored in the core is progressively released towards the outer shell. And the fact that the mantle, it's solid, but still can reach temperature up to 2000 to 4000 degrees, that allows that solid rock to become more fluid. Essentially, even if it's a solid rock, it can, under very slow geological times, so under very slow processes, that rock can actually flow as a fluid. And by slow, I mentioned, can give you a number, it's in the order of a couple of centimeters per year. So you can, if you fix a point in the mantle, that point will move after 1 year by 2 centimeters. And so that's the main principle of plate tectonics. So things can move around, and that's because of that high temperature that is stored in the core. So as I mentioned before, plates are all moving around our planet. And of course, imagine you are in a crowded market. If there is more and more people, you necessarily, at the end, you will interact with other people just by, just colliding with them. So like in a crowded market, tectonic plates move around the globe, and of course, they interact with each other. So the interactions are different depending on the relative direction of two plates. There is the first interaction you can see here. It's when the two plates are actually moving apart. we call that interaction a divergent margin. And at divergent margins, we actually create crust. So new crust is created at that location. It's what we call mid-ocean ridges, for example. So mid-ocean ridges crust is formed. When the two plates are actually converging towards each other, they necessarily have to be consumed. So if the plate on the right here, it's pushed towards the left, that necessarily have to go down underneath the other one. So this process is called subduction. So subduction only occurs at convergent margins, and at those kind of margins, crust is consumed. So whatever is created here will be eventually consumed at subduction zones. So at the end of this talk, I will talk about subduction more in detail. But for now, just let's keep this generic concept about plate tectonics. The third type of motion, the third type of interaction between plates is called a transform plate boundary. And at transform plate boundaries, plates are actually sliding next to each other without creating crust or consuming crust. So it's what we call a conservative plate margin. But the key point to keep in mind is that no matter how you move your plates, no matter what the speed of the plates are, the volume of our planet doesn't change. So it's like a Rubik cube. You can see here, so you can move the different places, the different blocks around, but still the volume will stay the same. So that means that whatever amount of crust you produce at mid-ocean ridges here has to be consumed at convergent margins. So that's one of the key principles of plate tectonics. So what is the effect of plate tectonics? The first effect, so the most evident, it's the generation of earthquakes and volcanoes. So whatever is dangerous, whatever is creating hazards and destruction, it's caused by plate tectonics. And that, so you can see here a map of the distribution of earthquakes and volcanoes. And if you compare this map with the map of the tectonic plate boundaries, you can easily realize that all the distribution here of the volcanoes and earthquakes actually describe exactly the distribution of the tectonic plate boundaries around our globe. So all this here is the mid-ocean ridge of the Atlantic Ocean. All this subduction, this is the subduction zone of the Pacific below North and South America. And on the other side of the planet, it goes, the same plate goes underneath the East Asia region. And in fact, we have lots of earthquakes in Japan and in that region of Philippines and New Zealand, for example. So earthquakes and volcanoes, they look quite pretty bad processes. So something that we don't want on our planet. So in fact, they can actually cause lots of destruction. So this is an image from one of the recent earthquakes in central Italy. And actually, there are still lots of people without home there. There are entire villages that has been wiped out entirely. So that's not very good for our life. I think we all can agree with this. But at the same time, if we look at the other side of the coin, we can actually realize how plate tectonics is good for our life. So one of the main effect of plate tectonics is the generation of mountain belts. So the fact that we have such a beautiful planet composed of mountains, valleys, creating this very beautiful sceneries, we have to be thankful to plate tectonics for that, because by collision, when two plates are actually colliding, they generate deformation, and that deformation is actually creating the mountains that we have around our planet. So that would be a pretty boring dead planet without plate tectonics. And if you again look at the positive things about plate tectonics, we can see that plate tectonics is also responsible for our prosperity. In fact, if we look at the last 200 years of economic development, it was the Industrial Revolution was mainly triggered by the discovery of a lot and cheap oil. So now we are in a new, probably different phase of our society, where we are looking towards different sources of energy, which is good. But still, we have to recognize that oil actually gave all the prosperity that we see today. So we made a huge improvement just in the last 200 years that has never been seen in the history of humanity before. And oil forms because of sediments are accumulating and organic matters. It's buried at depth and it's heated up by the other pile of sediments that are accumulating on top. So that whole process is actually triggered by plate tectonics. So again, without plate tectonics, we wouldn't be, I don't know, so rich or so, have all this wealth and economic prosperity that we have seen now. On the other side, again, more prosperity. If you think about metals that can be just, for artifacts or other, for example, gold is used in electronics as a conductor. So again, you can find gold because of volcanoes. So convergent margins in particular, where we have, if you remember the map of the distribution of volcanoes, there were lots of concentration of volcanoes at convergent margins. For example, all the belt of the Andes in Chile, Peru, and North America, the western coast. So all that margin, which is a convergent margins, there are lots of volcanoes, and volcanic activity also correlates the formation of ore deposits. So ore deposits could be just gold, silver, but could actually be some more less valuable, but more useful for our life, like copper, for example. So if you think about copper, we use copper everywhere in our daily life, from cables to other conductors, and just cables was the main, let's say, infrastructures that actually allowed to put the whole humanity in contact. Okay, so with telephones, and now we have internet, computers. But anyway, all this is again is correlated to plate tectonics. So we need to be really, really grateful for that. Okay, so this was a very brief overview of why plate tectonics and why is that so important for us. So now I want to describe how we actually arrived at the formulation of the plate tectonic theory, which is now considered one of the 5 biggest discovery in science in general. So it's one of the biggest discovery ever made, and there is no such a person that can be is responsible, can be let's say pointed for being the discoverer of plate tectonics, because actually the formulation of the plate tectonic theory was due to a number of people, and each one of those were actually contributing with a different little piece of the puzzle. And at the end, the whole puzzle came out together without one person specifically to put them together, the puzzle. It just came out and everybody realized that, and that was it. So that was the formulation of the plate tectonics. So it was a very joint effort from many, many scientists. And so in this brief overview, I want to just go over the history of how we arrived at the final formulation of the plate tectonic theory, which was in 1967. So we start everything with this guy, is Alfred Wegener, in 1915. So it was at the beginning of the century. And this guy was a German scholar. He was interested in natural phenomena, and he actually realized that continents, just putting together all the continents that you can see today on the planet, they actually fit pretty well all together, and they can actually describe a larger landmass. And we called Alfred Wegener called this landmass Pangea. So it's a supercontinent. And so he called that process, he mentioned that the continents can actually drift around the globe, and he coined that term as continental drift. Now, if you think about in 1915, when we didn't know much about how our planet was working, basically. So we saw mountains, we saw other areas, flat areas, high relief areas, deep valleys, oceans, but we actually didn't know how all this formed. So these guys started to mention that continents can actually move around. And so you can imagine about probably 90% of people thinking that this guy was just crazy. And they actually started to propose alternative explanation to that. But the evidence that actually Wegener used was pretty solid. So he used, for example, the distribution of fossils around the globe on different parts. And he recognized that by putting together all the different continents the way he did, those areas with similar, let's say, flora and fauna was actually quite consistent, forming very continuous belts like this one across Africa, India, and Australia, Antarctica. Or, for example, this other type of plants that were actually forming all across Australia, Antarctica, India, and Africa and South America. So everything was pretty much consistent. And also the shape of the continent was making a lot of sense to him. So it looked a very simple solution to the problem, but actually what he didn't know was the mechanism. So all people at that time was kind of attacking and criticizing Wegener for his crazy theory. And they were actually trying to explain the same evidence, because evidence are just evidence. So there is nothing to argue about that. But people was trying to explain the evidence in a different way. For example, the way why we find fossils, same fossils all across the western part of Africa and the eastern part of South America. Those people started to propose that there were probably some land bridges, very long, that unfortunately now has disappeared. For example, also here. But you can imagine that probably this theory is even more ridiculous than the Wegener's one. So this kind of critics were actually quite short-lived. But there were other people thinking, for example, that the whole planet was expanding. So if the planet started from a shape that was much smaller, composed of just continents, you can actually explain why the continents are today, they can fit all together just by following this mechanism. So they're just cracking due to the expansion of our Earth. But again, this is another pretty laughable theory for the expanding Earth that didn't last very, very long in terms of critics to Wegener's theory. So the theory just stayed there because basically there were no mechanism. So he realized he had this kind of vision that continents can actually drift, but he couldn't explain how. So if you think about this as the continent, we are not really, we are quite far away from the reality. So it's not just the continent that is drifting, floating on something else, but now we know it's the whole tectonic plate. But still, that evidence was pretty crucial for the next evidence that we collected after that. So one of the following evidence came a few decades after, so in 1949, with from two guys. There were two seismologists. The first one was a Japanese called Wadati, and the other was a German called Benioff. And those seismologists, they started to observe and measure earthquakes around the globe. And with the new technology, they could actually calculate the depth of the earthquakes. So what they started to measure, and in particular in the coast of Japan, was that they observed a number of earthquakes distributed along a linear, kind of a planar surface, going at depth and deepening the more you were moving inland from the ocean. So at that time, they could not really explain what the origin of those seismicity was. They just realized that there was a zone, a planar zone, where they observed a lot of earthquakes. And that zone was dipping about 45 degrees. And they tracked down earthquakes down to about 670 kilometers down at depth. So again, like Wegener, there was pretty much no mechanism to explain this. So they just collected data, they throw the data to the community, and pretty much no one could actually explain this because we didn't know anything about plate tectonics. So another 10 years after, so 1956, we are getting closer to the actual formulation of the theory. There were this time a guy working with paleomagnetism, which actually is my specialty. So it's the property of rocks to retain and record the geomagnetic field direction. So he used this Warren Carey. He used the paleomagnetic direction of continents to reconstruct the motion of the continents. So by looking, because the paleomagnetic direction has an inclination that depends on the latitude, by measuring different rocks of different ages from a plate that is moving, will actually give you directions that are at different inclinations that indicate that basically you're moving away or closer to the pole of the spin axis, to the geomagnetic pole. So that was another evidence that actually Wegener was right. So continents are actually moving. And this is a further kind of proof of that. So we have, again, lots of evidence. So fossils, shape of the continent. Now we have also the paleomagnetic data that are indicating the continents are moving. But again, we did not know how that was happening. In 1960, Hermann Hesse was actually the first one to explain how the oceans are created. And this was probably the most kind of important discovery that was one of the key elements of plate tectonics. So the formation of oceans. So according to this mechanism, so the seafloor spreading, he proposed that oceans were formed at cracks within lithosphere, and magma was actually rising up at those cracks, solidifying and being accreted to the new seafloor. And the two regions that we did not call plate at that time was actually moving apart to allow new material to come into this crack. Again, pretty much in the same time, between 1959 and 63, there was another very important data that came out from the oceans. And this data, it's the magnetic marine anomalies. So the magnetic marine anomalies are regions of the seafloors that are magnetized normally and reversely. So the magnetic field flips in direction periodically. So during normal polarity, which is what is today, the magnetic field is directed in a normal polarity. The rocks that are created at that mid-ocean ridge are magnetized in a normal polarity. And the more you move this ocean away from the mid-ocean ridge, you create a new rock, maybe during a reverse polarity period, that will be magnetized in a reverse polarity. So that process actually creates a number of bands in the oceans that are parallel to the ridge, and they are alternated polarity, normal and reverse. So this came from actually some instruments that they used during the Second World War to detect submarines. And they started to use that device to study our planet. And actually they realized that this was pretty much everywhere in the ocean. So they recognized all these bands of magnetic anomalies everywhere around the globe. But again, we could not explain what they were and how they were created at that time, until this guy, Fred Wine. Fred Wine was a professor, well, at the time, I think he was a postdoc. And what he basically realized is that by combining the seaflow spreading mechanism of Hermann Hesse with the magnetic anomaly just discovered, that you can explain pretty much one of the principles of plate tectonics. So without spending more words on this, I want you to hear basically how Fred Vine came to this conclusion by his own words. And there is a video here I want to watch. It's only short, it's probably a couple of minutes, and he actually explained what he discovered at the time.
Yes, the concept was first...
Frederick Vine explains his discovery. A connection between those magnetic reversals and Hesse's conveyor belt, which determines the speed of seafloor spreading.
Oceanic crusts at seafloor is continuously being created at mid-ocean ridge crests, such as the crest of the mid-Atlantic ridge here in the South Atlantic. It is generated above an upwelling in the mantle and spreads laterally away from the crests, thereby drifting the continents apart as though they were on a conveyor belt of upper mantle material. So one might represent this, therefore, by a simple model such as this, illustrating the way in which the conveyor belt of oceanic crust and upper mantle material flows out from this central crack in the Earth's crust. When in 1963, John Matthews and myself, then at Cambridge, added the simple rider to this, and in effect converted his conveyor belt of oceanic crust into a tape recorder, which suggested that as new crust is formed, solidifies at a ridge crest, frozen into it will be the current direction of the Earth's magnetic field. This will be subsequently moved aside as newer material comes in. And in this way, successive avenues of crust, normally and reversely magnetized, will be built up, paralleling the ridge crest and symmetrically disposed about it. And indeed, going back to the anomaly map, the very detailed contour map of Raffan Mason for this area of the Northeast Pacific, and after peering at it for some time, we could see that indeed there is a remarkable symmetry of the magnetic anomalies about the crest of this so-called Juan de Fuca ridge in this area, and they do indeed reproduce all the details of the reversal timescale in remarkable detail. So to summarize this then, we drew up this new colored summary map, which emphasizes this symmetry about the ridge crests in a truly remarkable way. It's incredible to think that it had been in the literature for 4 or 5 years. In 63, it was very frustrating because I had this idea and one realized that if it was true, you know, the implications were enormous. The ocean basins were young, ephemeral features, that all the oceanic crust, all the deep ocean basins that we see today were generated, say, within the past 200 million years of geologic time, less than 5% of the whole of geologic time.
Yes, so that was really inspiring. I mean, this whole, just thinking about the being at that time, you know, when all the discoveries were actually coming all together, but you could not figure out. I mean, you had some clues about what was going on, but still not very clear mechanism how to explain this. So at the same time, it would have been very, very excited to be, you know, a scientist at that time, to be, you know, part of this, one of the biggest discovery in geology. And so as Fred Vine said, the implications of this are enormous, because we did not know anything about the age of the oceans. We did not know how the oceans are formed, the structure of the oceans. We now know that there is a ridge crest in the middle of the oceans because it's where new crust is created. But at that time, there were not such information available. So we are getting very close to the actual discovery of the formulation of the theory is 1966. Excuse me. And it's Tuzo Wilson actually was the guy that proposed the so-called Wilson cycle. So the Wilson cycle, it's a very simple mechanism. What he suggested is that the evolution of our planet occur along a cycle that actually is repeated over and over and over the geological history. And it's composed of several processes that are key within this cycle. So if you start from the top is a stable, what we call a stable craton. So a craton is a stable area where there is no much tectonic process going on. Think about the, I don't know, the center of the African continent, for example. That's the craton. So at some point in the geological history, that craton became unstable and can actually split apart. And one of the examples of this splitting that we call rifting, it's actually in Africa, in the eastern part of Africa. So we are splitting that massive craton into two major pieces, the first one being in the east and the rest of Africa being represented by the other plate. So in a few million years, even Africa will be composed of two plates, and there will be an ocean in between. In fact, if you continue looking down into this cycle, from rifting, where we start pulling apart the continents, we create a new ocean in between. Okay, so the new ocean eventually will become inverted. So the process of expanding will stop, and we will start to contract the ocean. So the ocean will actually start to be consumed at subduction zones. So within this ocean, we create a new subduction, and that subduction zone, which is a convergent margin, accommodates the consumption of this lithosphere until the two continents that were once together, they are getting closer and closer, and they eventually collide again. Forming collision creates deformation. Deformation means mountains, orogeny, what we technically call in geology. And during the formation of the origin, the convergence is active, so we create massive topography. But when that force actually stops, that topography is erased. So basically, erosion will erode all the mountain that has been formed in this phase, and we go back to a craton. And this can be repeated many, many times over geological histories. So it's another very important process of plate tectonics, because it's actually, this contains all the elements, all the processes that can explain how our planets evolved through time. So I think we are pretty much there, because this was the final part of the puzzle. We in this, we can say between 1965 and 67, all this evidence combined together, we actually put them together into one big theory that was the plate tectonic theory. But there is not such a paper, as I mentioned at the beginning, or such a single person that can be considered the inventor of plate tectonics, because this was, as you have realized, it was pretty much a joint effort, and there were different pieces of the puzzle that naturally came together into one simple explanation that was occurring at that time, so 1967. So now we actually 3 years ago, I gave this talk at the university to a similar group of people. Probably some of you might have been there already. So this was pretty much a similar presentation. And at that time, I was actually giving this presentation because it was the 50th anniversary from the discovery or the formulation of the plate tectonic theory. We are still not far away from that, so 53 years. But I wanted to to show you what we, in this 53 years, what we have learned and what we have discovered, and what I will conclude by just talking about what still has to be discovered in plate tectonics. So if you look at this image, this is our planet. This is an image taken from Google Earth. And I just put the continents there to make you realize how big is the ocean. This is the Pacific Ocean. And this actually is taking up pretty much half of our planet. So half of our planet is composed of oceanic rocks, so ocean basins. And all this, it has to be discovered yet because it's underwater. So there is not much we can do. Well, actually, we can do something. We are doing the IODP explorations that was mentioned before by Christine. And I participated a couple of times in these expeditions at sea, where we actually drilled different regions of the oceans to understand specific processes of the solid Earth cycle. So what I want you to realize is that this ocean is vast, and what we know as a mechanism to create this ocean is what we can define as a magmatic mode of seafloor spreading. So there is two plates that are moving apart, material, mantle, which is solid, start to be uplifted and upwelled below this crack between the two plates, which is the divergent margin. And that solid rock melts to create a new magma, which eventually solidifies again at the surface, creating a new crust. And this process is repeated as long as the two plates are moving apart. So this is all the gaps that is created by the two plates that are moving is accommodated by the formation of new crust. So it's a magmatic mode. But in the last probably 20 years, actually, everything started in the beginning of the 90s, 95, roughly. We started to look at structures under our oceans, and in particular structures that are close to the mid-ocean ridge. So this is one of the image that is showing the what we can find under or close to a mid-ocean ridge in the Atlantic. You can see from this image that we have this huge area that it's, you can realize it's a kind of a dome-shaped area. It's pretty big. This is the scale, it's 1 kilometer. So we're talking about probably 10 kilometers of width. And you can see this remarkable structures all around the surface. So it's a very smooth surface, but with lots of scratches. Those scratches are actually a sign that this is a fault. So in geology, we're well aware of the structures at the small scales. They have different name, but it's very typical of faults. So when two blocks of rocks are moving relative to each other, they slide next to each other and they create those scratches. So by looking at those images in the early 90s, we realized that this actually are massive, massive faults. And something that we did not expect to find at the bottom of the sea, actually. So everything was supposed to be, created by normal magmatic, what we call magmatic accretion. So we were not expecting faults at all. But actually, once we have started to look at those structures, we went to different regions, and we actually started to look exactly the same features in other parts of the mid-ocean ridge. And basically, that simple observation allowed or triggered other studies until we actually formulated a new model for mid-ocean spreading. So in particular, that region that it's composed of scratches is a fault, as I mentioned, is what we call oceanic detachment faults. And that fault actually bring deeper rock, which are mantle rocks, to the bottom of the sea. So where we should expect to find just lava, which is composed of crust, is the main component of oceanic crust. So just summarizing that process in this block diagram, we have a spreading ridge here, which is the red line. When the two plates are moving apart, so this block is moving to the right and that one to the left, actually there is very little production of melt under this spreading ridge. But because the two plates are moving apart, we cannot leave a gap in that region. So all the divergence, all the stretching is actually accommodated by creating those massive faults. So those oceanic detachments. And the oceanic detachments are bringing material that is there up to the bottom of the sea. So this is a map of a very small segment of the Atlantic Ocean, and the stars represent actually the single detachment faults that has been observed. And again, this is the scale of this. It's 50 kilometers, so we're talking about 200 kilometers. There are plenty of them. And so we pretty much can be sure that those structures are indeed everywhere in oceans like, for example, the Atlantic. And the big discovery was that actually in the whole Atlantic is not created, well, mostly by not magmatic activity, but by tectonic activity. So the extent of the Atlantic Ocean is pretty much created by those very large faults that continuously create at mid-ocean ridges. So we have now another, so this is probably the biggest discovery in earth sciences since the beginning of the formulation of the plate tectonic theory, and came after about 30 years after the discovery of plate tectonics. So scientific drilling, again, we can observe this, as I mentioned before, because we actually are able today to explore at least part of our vast ocean. And the images that I showed you before about this big fault was taken by one of this big ship that actually navigate and collect continuously data from our ocean basins. But so we can say that oceanic detachment faulting and this kind of what we can call a tectonic mode of seafloor spreading, it's something that we see today. But is it also, we can ask a question whether is this something that was operating also in the past? So is it something that occurs only recently, or was actually occurring at every time in the geological past? Well, we have the solution now, because we also explored this pieces of oceanic crusts that are preserved on continents, and these red blobs are what I'm talking about. So these ophiolites are called, so are spreading ancient fragments of oceanic crust that are today exposed above sea level and on top of continents. So we can simply, rather than taking a boat, spending millions and billions of dollars to make an expedition, we can simply go in the field and collect data. So one of the important constraint about this mechanism of seafloor spreading came from this region here in the Balkans, in particular in Albania, where actually, despite the name of this region, this particular city, which is very lovely, I spent about a couple of months there to do field work. That region preserved a Jurassic ophiolite, so it's about 170 million year old ophiolite. And what we can see there is a structure that is composed of mantle rocks surrounded by lavas. And the shape and the size of that structure, that dome, it's pretty much resembling that of oceanic detachments, what we call oceanic core complexes. And the rocks that appears there are actually, there is a very little crust, even in that region, which is again expected for a detachment mode of seafloor spreading mechanism. But we did not have many quantitative data to really support that idea. So we can only speculate that this was an oceanic detachment faults until we collected data that could actually prove that. And in particular, this is a simple explanation of what oceanic detachment faults are doing in terms of deformation. So imagine you have some reference data that could be anything. This in particular could be a paleomagnetic direction, so the record of the magnetic field. So before deformation, before faulting, that direction of the magnetic field is equal everywhere within this piece of continent of a lithosphere. When this fault start to operate, which actually allow all this region to rotate along a horizontal axis. So the more you rotate this region, the more the two reference direction are displaced. So by using the simple approach, we collected paleomagnetic data from that region, and we actually realized that indeed the whole mantle region is rotated by 45 degrees, similarly to the rotations we actually find today in the oceans. And this is a Jurassic piece of oceanic crust. So we arrived at the conclusion that this actually detachment mode of seafloor spreading is a mechanism that operates today in the oceans, but actually operated as well in the past, up to at least the Jurassic. But we can actually assume that it was always operating since the pretty much the beginning of plate tectonics. So this is a massive discovery in terms of how our oceans are formed. And we did not know anything about this until 25 years ago. So again, this is one of the probably the biggest advance in scientific discovery in geology since the formulation of plate tectonics. So I will conclude now with the final part, talking very quickly about future questions. So what, and in particular, I will talk about one of the processes that still are relatively unclear that operates in our planet, and it's subduction. So how subduction are actually starting. So how we start closing an ocean from an original spreading ocean. And so how do we switch that motion from expanding to contracting? And that's a big question. If we look at today, the subduction zones in our globe, this is all the locations where we have convergent margins, so where oceanic crust is consumed, and the color is the age of those subduction zones. So you can see that those subduction zones are at different ages. So they are not just concentrated in a particular period of time, like for example today or in the past, but they are actually occurring continuously on our planet. So it must be a process that actually is quite easy to achieve, and it must be a process that can easily occur and can repeatedly occur on our planet. However, we do not have any modern example of how a subduction zone is formed, and that's because the geological process it's, we can say, geologically instantaneous, but still it can take 3, 4, 5 million years. So it is something we cannot observe today with our measurements. So we can see clues of that, but not be sure that subduction is actually starting in a location. And so where the key question, there are several key questions about subduction initiation. And one of these is, where can subduction start? So if you think about if you have to break something, if there is already a pre-existing crack, that material will keep cracking along that fracture. So that fracture can create what we can define a weakness. So to start a subduction zone in an ocean, we can easily suppose that that will occur in regions where we have a pre-existing weakness. So the weaknesses in the oceans are several, and here is a kind of a list of those. We have ridges in red, so the spreading ridge, which is this crack within the lithosphere. The connection between the different ridge segments is called transform. So we have transform faults that can be very wide, like this one. And we have detachments excuse me, next to the ridge. And we have the prosecution, the transforms that are called fracture zones. So you can actually see how this continues laterally. So all these fractures are weaknesses. So we can expect subduction to start along those weaknesses anytime. As soon as you have an external force to trigger that mechanism. The second question about subduction initiation is how. So how does subduction start? So we can have two competing mechanisms or two possible mechanisms. The first one being a forced mechanism, where you have an ocean between two continents, and basically you simply apply an external force, which could be a tectonic force coming from another region that actually create that crack or use an existing crack to create a new subduction zone. So the second mechanism is what we call a spontaneous mechanism. And that mechanism actually does not need an external force. So no, it does not need a tectonic force to be triggered, but uses the gravitational force. So the gravity force, for example, in cold and more dense oceanic lithosphere, we can expect it to sink simply into the mantle that might be hotter. So that process is kind of mentioned in the literature as a spontaneous mechanism, and it can operate at the continent-ocean boundary, like here, but can also operate at mid-ocean ridges along transform faults. If you see a cross-section of this region, a transform, you can see that there are cold and denser lithosphere just next to a hotter and lighter lithosphere. So the colder one will probably naturally sink into the mantle to create a new subduction zone. But as I mentioned before, so this mechanism is geologically quick, but for our human life, it's still a long process. So we cannot see any modern example of this process. We have two examples of possible subduction initiation, and one is in south, in the offshore of Portugal, in the Gibraltar Arc. That was actually, there are some evidence from seismicity that we can have some convergence, some convergent forces operating there, creating lots and lots of faults that we are not expecting. And another region is the New Zealand, where we have a region of the seafloor that is actually deforming today. It's been uplifting progressively in the last few years, and that's probably because one of the Indian Ocean is actually subducting, beginning to subduct below that region. But again, it's very slow, so we can only speculate that that is the case. But still, we don't know what's going on out there. So the way to study subduction initiation, the way we can tackle this problem is by, again, using ophiolites, because we have so very little examples of modern oceans where this process is occurring, and it's not very accessible. But we can use actually ophiolites to study that. And that's because ophiolites are actually formed during the beginning of a new subduction zone. So imagine this, the ophiolite is this red region. We actually invert this ocean, we create a new subduction zone, and at the same time, we create this ophiolite at the top. So by looking at that, that might have recorded, this ophiolites might have recorded this process. And in fact, we, a few years ago, by studying again the Balkan ophiolites of Serbia, Albania, and Greece, we came out with a new model for subduction initiation that used oceanic detachment, the one that are actually helping oceans to expand for example, in the Atlantic. So according to that model, that oceanic detachments that are here, these little tiny lines, can actually create the sufficient weakness to accommodate convergent at or very close to the mid-ocean ridge, which is this other thick line here. And that's because inverting or creating a subduction at this region has been demonstrated to be very difficult, if not impossible. So at some point we observed that subduction in different period of the geological time must have started close to a spreading ridge. And this actual model provide the right mechanism to have that subduction zone close to the ridge. So another discovery that will actually will probably put another piece of the puzzle of subduction initiation for the future. And with this one, I think I've concluded. So I really thank you for your attention, and I'm